You know, when you picture heavy-duty machinery or robotic arms, the first thing that comes to mind is just absolute rigidity.
Right.
Solid steel, thick I-beams, things that absolutely do not budge under pressure.
Yeah, we naturally equate stiffness with structural integrity. I mean, unbending means safe.
Right. But if you look inside the precision joints of a modern robot, that entire rule book is just tossed out. We're zooming into this microscopic landscape where metal is explicitly designed to warp and flex.
It really is a totally different world.
It is. So, welcome to this custom deep dive into your engineering notes on precision transmission. Our mission today is to decode the complex physics inside these joints and figure out how they achieve something paradoxical, like getting massive power out of incredibly tiny, lightweight spaces.
And shedding weight is, well, it's the holy grail here. Usually to get a massive drop in speed and generate high torque, you'd use a bulky, multi-stage planetary gear system.
Which takes up a ton of room.
Oh, absolutely. It's huge. But in precision robotics, they use single-stage reduction. They can hit extreme speed drops, like 100 to 1, with just a single gear pair.
Okay, let's unpack this. Because these notes are basically the secret blueprint for modern robotics. How do you get a 100 to 1 reduction in one stage? The secret lies in the math, right? Specifically, a tiny discrepancy in the gear teeth.
Exactly. You have a rigid outer ring, the circular spline, and a flexible inner cup, which is the flex spline.
Right.
And the difference in the total number of gear teeth between them is usually just two. Just a difference of two teeth.
Wait, really? Just two?
Yeah. If we connect this to the bigger picture, that tiny fractional difference relative to the total teeth is what mathematically generates that enormous reduction ratio. Every full rotation of the motor only advances that flexible inner cup by that microscopic two-tooth margin.
That is wild. It's kind of like turning this microscopic dial that somehow moves a massive heavy door. Just this compounding tiny offset that gears down the speed and aggressively ramps up the torque.
Which, brings up an immense physical challenge. Because all that intense torque is happening in just one stage.
Right, it's all concentrated.
Exactly. With standard spur gears, only a couple of teeth actually touch at any given time.
And if you tried to pass this much torque through just two teeth, they'd instantly shear off.
They'd be completely destroyed, yeah.
Yeah.
So you need more teeth touching. And you can't do that if both gears are perfectly round and rigid. You have to imagine a flexible metal cup sitting inside a rigid metal ring.
Okay, I'm picturing it.
An internal elliptical plug physically forces that flexible cup to bulge outward into an oval shape. And because it's an oval, the teeth on the long ends, the major axis, are the only ones mashing into the rigid outer ring.
Oh, I see. That geometry allows up to 30% of the total teeth to engage simultaneously, right?
Right. That wide engagement area spreads out the load, which creates extreme torque density without ripping the system apart.
But you can't just bend a solid metal cup in the middle of nowhere. I mean, it's anchored at the base.
It is.
So when the open end is pushed out into that oval by the internal plug, you aren't just getting a cylinder anymore. You are physically distorting it into a cone that's conning.
Yes, conning. And what's fascinating here is that designers absolutely must mathematically compensate for this coning effect. Because the base is fixed and the top is forced outward, you get severe localized stress right at the open end.
Right, because the metal is sloping.
Exactly. If they don't account for how the metal slopes, the steel will just fatigue and crack under the strain.
Here's where it gets really interesting. Wait, hold on. If you're rapidly stretching metal into an oval, bowing it into a cone, and forcing these teeth together, isn't there a huge risk of the gear teeth just smashing into each other at high speeds?
Oh, absolutely.
Like, wouldn't they just grind to dust?
That is the exact nightmare scenario. To prevent that catastrophic clash, engineers have to calculate the radial displacement down to the micrometer.
Radial displacement. So that's the exact physical distance the flex spline is pushed out.
Right. They need to know that precise physical distance the metal cup is bowing outward. Calculating this exact radial displacement dictates the mesh depth.
Oh, wow.
And perfecting that mesh depth is just completely necessary. It's non-negotiable.
So it has to be absolutely perfect to prevent tooth tip interference when the machine is operating at high speed?
Exactly, tooth tip interference. If they get the stretch wrong by even a fraction of a millimeter, the teeth clash instead of locking smoothly, and the joint destroys itself.
Unbelievable. So what does this all mean? For you listening right now, understanding these specific physical interactions completely changes how you look at a robot. It transforms a basic robotic joint from this mysterious black box into an absolute masterpiece of controlled material strain and geometry.
It really is. It's a symphony of controlled deformation. Every single bend is meticulously calculated.
It really makes you wonder. We started by talking about how we expect heavy machinery to be perfectly rigid. But if precision robotics relies entirely on forcing rigid metal to bend and flex, literally turning a structural weakness into a massive mechanical advantage, what other traditional rules of engineering could we completely flip upside down just by changing how we look at materials? Something to think about next time you see a robot in action.